Um, yeah, I hope the screen is visible. So we'll be talking today about urea kinetic modeling. So before we begin, just a few small disclaimers. So this will actually not be on your exam. This is just something which interested me. So I read a little bit about this and I just wanted to share. I put it together in a simple way so that hopefully it will make a little bit of sense. So there are no fish tanks in this talk. I know when I was preparing for this as a PG, that chapter kept on talking about the fish and the tanks, and that drove me slightly crazy. So I'm not going to be talking about any fish tanks during the session. A lot of this I don't understand fully myself. I've just read from a couple of places and I've put it together. I think this is still a very important topic though, because it forces us to think about some of the core principles of dialysis. And dialysis, of course, is our bread and butter. So I think we should know as much as we can about the procedure. So this is from Nissensen's. So he starts with this. He says nephrologists should assess the dose of HT that they are prescribing by periodically measuring it. So this is a reminder to us that dialysis is not something qualitative. It's not that, okay, I dialyzed him yesterday, today I'm spacing, and tomorrow he's due again. So that is a qualitative assessment of dialysis. It's like saying somebody who has acid peptic disease, I've given him pantoprazole. So that is qualitative. So what we want to say is we've given him 40 milligrams of panto twice a day for 2 weeks. So that is quantitative. So we are actually measuring the dose. So similarly for dialysis also, it doesn't come automatically. You have to actively go and measure it yourself. And nephrologists should be measuring the dose of dialysis, which they are prescribing to their patients. So history of medicine actually interests me quite a lot. So we'll start with the history of this. This is the NCDS paper from 1981. And this is where it started in 1981. So before we go into this paper, we'll be looking at some of the trials and the studies which have led up to the current accepted standard of KT over V of 1.2. So before we go into that, I just want to talk a little bit about this last author on this paper, Dr. John Sargent. You'll find that it says PhD there. So he actually died recently in 2020, and this is his obituary in Kidney International. And you'll find that the obituary was actually written by Dr. John Daugirdas himself. Actually, he's not a medical doctor. He is a chemical engineer by training, and then he got his PhD. In fact, his PhD thesis topic was the role of acetate dialysate and its effect on acid-base balance in patients on maintenance hemodialysis. So this was a chemical engineer basically, but he knew more about dialysis than I think a lot of physicians themselves do. He died at the age of 81. And what's interesting is that he continued to write papers and continued to do research even after he retired. In fact, the last paper which he published was published posthumously, meaning it was in peer review when he died. So actually that last paper is reference number 5 on this obituary. And I think you should go and read this if you can. It's a very piercing critique of another paper on dialysis, which is very fascinating to read. Anyway, so this is the NCDS paper from 1981. So this is basically a 2x2 factorial. This is basically a 2x2 factorial trial design. So for anybody who doesn't know what a 2x2 factorial trial design is, basically each patient is randomized twice. All right, so they get one randomization followed by a second randomization, and then you look at the outcome. So the beauty of a 2x2 factorial trial design is that you can assess independently the effect of the first randomization on the outcome and the effect of the second randomization on the outcome. So you can basically do 2 RCTs in one by using a 2x2 factorial design. So in the NCDS, what they did was the first randomization was either a high average BUN of 100 versus a low average BUN of 50. So you got either dialysis targeting a BUN of 100 versus a dialysis targeting a BUN of 50. Second thing is you achieve this target by getting dialysis either for 3 hours or for 4.5 hours. So basically now there are 4 groups. You could get a BUN, you would be randomized to either BUN of 100 with dialysis of 3 hours, or BUN of 100 with dialysis of 4.5 hours, or BUN of 50 with dialysis of 3 hours, BUN of 50 with dialysis of 4.5 hours. And then you looked at the outcome, which was treatment failure. So what they found was the people with higher BUN, they actually had greater risk of treatment failure. So a lower BUN obviously is better. So that was the effect of randomization 1. Randomization 2, it actually didn't reach statistical significance. So they were both equal. But for people who got a longer amount of dialysis, so people who were randomized to 4.5 hours, there was a trend towards benefit compared to people who got 3 hours. So basically, the NCDS trial is telling us targeting 50 is better than targeting 100, and doing 4.5 than doing 3 hours of dialysis. So this was the NCDS from 1981. So, but the legacy of the NCDS comes from this paper from 1985. So this is the mechanistic analysis of that NCDS data. And again, this was by Frank Gotch and Dr. John Sargent. So they said it's actually not the urea level which matters. It doesn't matter if it's 50 or 100. What matters is this thing which they call the KT over V. And this is where this KT over V concept was introduced in this paper. So this is actually a measure of clearance of urea during dialysis. So he says it's not the absolute value of urea, it is the clearance of urea during dialysis which matters. And when this KT over V is less than 0.8, you get treatment failure. When it is more than 0.9, you're okay. There's no chance, there's no risk of treatment failure. In fact, they found that if you go above 0.9, if you go 1.2, 1.3, 1.5, there's no added benefit. So 0.9 is sort of it's this way or that way. 0.8 and below, you are at high risk of treatment failure. Anything above 0.9, you are okay. So that's where their target came as, they said you should be targeting a KT over V of 1.0. You want it to be more than 0.9, so you target 1 is what they had recommended at that time. The other inference from this paper was that patients with a low NPCR, and we'll come to this NPCR and this KT over V, and we'll talk about this a little later. But low NPCR basically means somebody who is malnourished. All right, so they said the people who are malnourished, they actually did badly irrespective of the dialysis dose. So it doesn't matter whether you got good dialysis or bad dialysis. If you are malnourished anyway, you're going to have a bad outcome. So this was 1985. This was where they introduced KT over V, and they said less than 0.8 is bad, more than 0.9 is good. So the next thing came in 1993. This is by Dr. Keshavaya. Again, this is a very interesting person. We'll come back to him. There's a story about that as well. So what he did was he reanalyzed the same NCDS data, which Gotch and Sargent analyzed in 1985. So he went back and saw that same data, but he reached a different conclusion. So Gotch and Sargent, if you remember, they said more than 0.9, it doesn't matter. Everybody is okay. Here they said the more you go above 0.9 all the way up to 2, you get added benefit. So in fact, there's an exponential decrease in treatment failure as the KT over V increases all the way up to 2.0. So you'll find that they're both looking at the same data and they have reached two different conclusions. One is saying it doesn't matter if you go more than 1, it's all the same. The other guy is saying you should go all the way up to 2. So this obviously required that you need to do another trial. And that's where you got the chemo study from 2002. And you'll notice again, Dr. John Daugirdas is one of the authors of this paper. So the reason why this trial was done is a lot had changed. So the NCDS happened in 1981. This trial is published in 2002. In this time, they have moved from Cuprafan dialyzers to more modern dialyzers. The technique of dialysis was better. Older people were getting dialysis. There were more people who were diabetic who were getting dialysis. And 2 people had looked at the NCDS data and reached 2 different conclusions. So we needed a new trial, and that was the hemo trial. So again, this was a 2x2 factorial trial design. Again, they got 2 randomizations. The first randomization was to answer that question, which is better, 1 or 2. All right, so they targeted 1.2 versus 1.6. Does it make a difference going above what is considered adequate? Second randomization was, do you get low flux versus high flux dialyzer? Do you have any benefit? And they were looking at all-cause mortality. So what they found was, it doesn't matter if you go more than 1.25. So people who got 1.65, they actually did not have an improvement in mortality. So 1.25 seems sufficient. There's no point in going above that, and we'll come back to why later. About the flux of the dialyzer, again, this also had no effect on all-cause mortality. So it didn't matter if you were using a low flux or a high flux dialyzer, your all-cause mortality was not altered. So the conclusion from hemo was 1.25 is enough. You don't need to go to 1.65. And the flux of the dialyzer did not seem to matter with respect to mortality. So to summarize these findings now, NCDS in 1981, a higher time average urea concentration had bad outcomes. So this was looking at concentrations, absolute value. The 1985 mechanistic analysis, Gotch and Sargent, this said adequacy is better defined by solute clearance. So that is by KT over V rather than absolute solute levels. And finally, the third thing was the hemo trial in 2002. They said the minimum dialysis, which we were saying 1.2, that also appears to be optimum. So there's no point in going higher than 1.2. So this was the data as it stands. So now I want to talk about formal urea kinetic modeling, but before we go into that, we'll need to go over a few key concepts. We'll go over these 5 concepts, and then we'll talk about how you model urea kinetics. So the first concept is uremia. All right. So let me just ask this question. I mean, you can put it in the chat box. When a patient has high potassium, we call it hyperkalemia. When a patient has high urea levels, do we call it uremia? Uh, do
False.
it. So you can maybe just put that in the chat box. Let me just, yeah, I don't think I can see the chat box. Um, Hang on. All right, okay, I don't think I can see the chat box. So hopefully most of you would have gone with false because the answer is false. So when somebody has a high potassium, it is called hyperkalemia, but a high urea level does not mean uremia. So what does a high urea level mean? It means azotemia. So the word we use when the urea level is high is azotemia. We don't use the word uremia. So where does this word uremia come from then? Uremia basically comes from the root word. There is urine in the blood. So uremia comes from urine, not from urea. And why do we say urine in the blood? Basically because urea is not the mediator of uremia. Urea is actually a very mild toxin. It is not a uremic toxin. So the syndrome of uremia is mediated by all of those uremic toxins, which we know about: small solutes, middle molecules, protein-bound molecules. Those are what is usually found in urine. And when that is there in the blood, so when there is urine in the blood, that is known as uremia. Urea is just azotemia, which means too much nitrogen in the blood. Why this is important and how do we know that urea is actually not that important in the syndrome of uremia? Because they have actually, this paper from 1972, they were dialyzing people. They added urea to the dialysate. All right. So they were giving them dialysis, but they maintained the blood urea levels very high. And this was to the tune of 150 to 300 milligrams per deciliter. So they didn't allow the urea to come down, but they gave them dialysis anyway. And they found that maintaining people with high urea, this did not actually cause any of the uremic symptoms such as encephalopathy and so on. So urea is basically not the cause of uremia. So then how do you diagnose uremia? It is basically a clinical diagnosis. You cannot diagnose uremia based on biochemistry because we don't measure any of these other solutes, which are the uremic toxins. We measure only urea. So we can actually biochemically call it azotemia. Uremia is a clinical diagnosis. So when somebody has renal failure and they have encephalopathy, you say, okay, this is probably uremia because we don't measure any of the actual mediators of the uremic syndrome. So if we say urea is not the mediator of uremia, then what is the mediator of uremia? This is another paper which I think any of the final years, if they're on the call, they should probably go and read this paper. See, Jason, I'm sure you've already seen it. So this defines what is a uremic solute, what are the uremic solutes that we know about, what causes what. So basically the highest evidence for uremic toxins are all of these: P-cressyl, sulfate, beta-2 microglobulin, IL-6, TNF-alpha. Thing is, we don't measure any of these, and you'll find that urea is not on this list. So urea is not a uremic toxin, but the actual toxins we don't measure. We do not know to what extent each of these contributes to the uremic syndrome. We can't obviously be measuring all of them. So we basically use urea as a surrogate for all of these things. So we actually do not know what is the biochemical basis of uremia, and we are unable to quantify it, which is why we look to urea. So key concept number 2 is what is the significance of blood urea levels? Um, so number 1 is at best it is a mild toxin because I told you they've loaded urea into the dialysate and nothing bad has happened to the patients. The second thing is the very fact that urea is allowed to build up to such an extent. For example, if somebody is very uremic, their creatinine, normal creatinine is 1, right? 1 milligram per deciliter. Once their creatinine touches 15, they automatically become very symptomatic. So 15 itself is very toxic when it comes to creatinine. But for urea, normal urea itself is 40. And you have people with 185 urea and all who come walking to your OP. So the very fact that urea builds up to such an extent and you can have people who are relatively asymptomatic at such high levels, that itself indicates that it is a mild toxin. Single blood levels of urea are actually difficult to interpret. So for example, if your urea level is low, um, then it can mean two things. One is you've either dialyzed them very well, so their urea level is low. The other thing is maybe they have simply not, they have very poor nutrition. So their urea generation itself is low. So these are two different things which have two different prognoses. If you dialyze them very well, then that means it's a good thing. But if they are so nutritionally deprived that they are not able to generate urea, then that's a bad thing. So that single value of low urea, you cannot actually interpret it by itself. Again, when the blood urea level is high also, it could be because of renal failure, it could be because of underdialysis, it could also be because of a GI bleed, it could be because you were giving the patient steroids. So there's so many different things which affect urea levels. So single levels are actually difficult to interpret. Urea is a poor marker of uremia. So as I said, the syndrome is actually because of all of those toxins which we do not measure. And urea by itself is a poor marker of uremia. And this is a very interesting sentence from Henrich. He says, many nephrologists and non-nephrologists have this misconception that BUN causes the uremic signs and symptoms, and that dialysis is essential if BUN is more than 100 or if urea is more than 200. This is false. At the same time, when BUN is low, it is often ignored. Again, this is a mistake. He says some patients have died a uremic death with a BUN as low as 50. That is a urea of 100. So you can die of uremia when your urea is relatively low. This happens when we disregard the, when we fail to notice that urea is actually a poor marker of uremia. So that is number 3. And finally, so if urea is a bad marker of uremia, why are we bothered? Because urea clearance is actually a good marker of dialysis. So even though urea doesn't define uremia, if you remove a certain amount of urea, the assumption is you are also removing all of those uremic toxins which we are not measuring. So the clearance of urea is actually a marker of the amount of the adequacy of the dialysis which you are providing. So though urea is a poor marker of uremia, urea clearance is a good marker of dialysis. I hope that's clear. I don't want to repeat myself too many times, but that's something which is very important to understand. And I can't see on the chat. So like if anybody has anything, you can please interrupt me at any time. So key concept number 3, what is so special about this molecule, urea? So there are certain properties of urea which are relevant to urea kinetic modeling. Number 1, it accumulates more than any other organic solute. As we said, even when it goes to 180, 190 and all, people are relatively asymptomatic. The fact that it accumulates so much itself is that it is a mild toxin. Second is it is produced by zero order kinetics. So what does that mean, zero order kinetics? It means that it is independent of the current urea concentration. So irrespective of whether presently urea is 50 or 100 or 200, urea generation happens at the same rate. So urea generation is actually independent of the current urea concentration. On the other hand, when you're doing dialysis, when you're removing urea, that dialysis urea clearance is actually first order kinetics. So you're removing urea by first order kinetics, meaning if your urea is very high, you are able to clear a lot more. If your urea is very less, then you're able to clear a lot less. So dialysis actually is first order kinetics, where the amount of clearance depends on the concentration of urea, but the production is by zero order kinetics, where the amount of production is independent of the serum urea. The third one is the distribution of volume, is the total body water. So basically, urea is freely permeable. I mean, wherever there is water in the body, in all of those places, urea is also there because it can move between cell membranes, it can move across compartments. It's not limited to the plasma. It can be in the muscle, it can be in the bone. So the distribution, so wherever there is water, at that place, there is also urea. So the distribution of urea is equal to the total body water. And finally, it is also easily dialyzed. So it is polar, it's water soluble, it's uncharged, it's not bound to any proteins, and the molecular weight is small. So since it is easily dialyzed, it is taken as a surrogate marker of the other uremic solutes. So now we come to this complex concept of KT/V, or what is clearance. So this is again from that mechanistic analysis, Gotch and Sargent from 1985. He says the mechanism by which dialysis controls BUN. All right, so the mechanism by which the amount of dialysis you're giving, so the mechanism by which dialysis controls BUN in an individual patient can be quantified from the total urea clearance prescribed, that is the KT/V, which is given by the product of the dialyzer urea clearance K and the treatment time T. And this parameter can be generalized by normalization to the urea distribution volume V. So we'll see what that means. So this is basically the ratio KT/V. So what is K? K is basically clearance. And what does clearance mean? Clearance is basically the volume of plasma per unit time from which all of the substance is removed. So the volume of plasma per unit time from which all of the substance is removed is clearance. So for example, if I say 2, a clearance of 2, it means I'm clearing 2 liters of plasma every hour. And it doesn't matter whether that plasma has a urea of 200 or 300 or 50, but I'm clearing all of the urea in that 2 liters of plasma. All right, so that is clearance. Next, T is the time on dialysis. So now if I'm saying I'm having a clearance of 2 liters per hour and I'm doing dialysis for 2 hours, then the total volume I have cleared is 2 into 2, 4. All right, so the numerator here is the total volume that I have cleared. So clearance is the volume per hour, volume per unit time. KT is the total volume which I have cleared during dialysis. So 2 liters per hour for 2 hours would be 4 liters. So the numerator is the total volume of plasma that I have cleared during that session of dialysis. And then I divide that by the total body water, which is the urea distribution volume. All right. So now if I say KT over V of 1, what does that mean? KT over V of 1 means the numerator here is equal to the denominator. So that is the total volume that I have cleared. KT we said is the total volume which I have cleared. So the total volume is equal to the total body water. So what that means is when I say a KT over V of 1, I mean I have cleared the total body water once. So and if I say a KT over V of 2, it means I have cleared that patient's total body water twice. So that is the meaning of KT over V. Uh, I hope that made sense. If that didn't, please let me know. So the next thing we have to understand is why it is important to normalize this. All right, the reason we normalize it to that patient's total body water is so that it is comparable across the population. So if I give somebody a KT over V of 1, irrespective of whether they are 10 kg or 70 kg, if I've given them a KT over V of 1, it means I've given them the same amount of dialysis. So now assume now you have two people, one with a 10 kg person and one with a 70 kg person. Both of them I've given them a KT over V of 1, meaning I've cleared their total body water once. The 10 kg person I've cleared actually 10 liters only, right? Because I've cleared their total body water once. 70 kg person I've cleared 70 liters, which is much more than 10 liters. So even though the volume I've cleared is different, the KT over V is still the same. So the amount of dialysis I have done for both patients is the same. So that's why we normalize it to that patient's body water so that it is generalizable. So it doesn't matter if it's a child or an adult or a male or a female. If a KT over V is 1, it means I've cleared that patient's total body water once. So the next thing we have to understand about clearance is that it is a measure of the elimination process, which is independent of solute concentration and solute removal rate. All right, so it's independent of both the solute concentration and the solute removal rate. So let's look at this example now. There's patient A and patient B. The urea is 200 here and 100 here. They both get 4 hours of dialysis. They both get the same amount of dialysis. So KT over V is 1 for both of them. They both weigh the same. At the end of that dialysis, urea becomes from 200 to 100 here, 100 to 50 here. All right, so they both receive the same amount of dialysis. But look at the amount of urea I've removed. From 200, it's gone to 100, so I've removed 100 milligrams basically. Here from 100, it's gone to 50, I've removed only 50. So it seems as if I've dialyzed this guy less. But actually, it's the same because KT over V is the same, and that is independent of the initial urea. All right. So KT over V now is independent of the solute concentration and the solute removal rate. It just means I have cleared the entire total body water once when I say KT over V of 1. And that is true irrespective of whether the urea is 200 or 100 to begin with. So clearance is independent of the solute concentration and the solute removal rate. The next thing to know about clearance is this very important graph. So on the x-axis, you have clearance KT over V. And on the y-axis, you have the amount of solute which has been removed. So once we have 0.5, so I've cleared half of his total body water, I've got rid of 40% of the urea. Once I double that, once I go to once, so I've cleared the total body water once, I've cleared around 60% of the body urea. The thing is, once I double this from 1, if I go to 2, it doesn't mean that the amount of urea I've removed also doubles. Because by the time I get to 1, I've already cleared 60%. So there's very little left. So doubling the amount of clearance does not actually double the amount of urea removed because most of it is already gone. There's very little left. So the incremental benefit of increasing the amount of dialysis in terms of urea removal is actually less. All right. So this is also something to understand that this self-defeating aspect of IHD. So as you increase the clearance, the actual amount of solute you remove becomes less and less. So this is important to recognize because once the dose reaches that minimum standard for adequacy, which we take as 1.2, somewhere around here, so that's around 70% of the urea which is removed. Once it touches that, increasing per dialysis KT over V further does not necessarily improve the outcome. And this is probably why in the hemo study, even though we increased the KT over V, there was no actually tangible benefit on mortality, because this is the self-defeating aspect of clearance in terms of intermittent hemodialysis. I hope that made sense. So the next thing is the determinants of clearance. So we've spoken about the qualities and the properties of clearance. So next is we need to know what determines clearance. So I've not mentioned the time. Obviously, that's a very important factor. The time on dialysis is important. But in addition to that, QB, QD, and the K0A. So QB and QD are basically the blood flow rate and the dialysate flow rates. So what's important to understand is clearance can never exceed either the blood flow rate or the dialysate flow rate. So if your blood flow is say 100 ml per minute and you are removing all of the urea in that blood, then your clearance is also necessarily 100 ml per minute. Your clearance cannot be more than the blood which you are being supplied. At the same time, if your dialysate is completely saturated with urea by the time it makes that one pass across the dialyzer, then you are achieving a clearance equal to the dialysate flow rate. So you cannot exceed the blood flow rate or the dialysate flow rate with your clearance. So clearance is limited by these two entities. The second thing is your K0A. So K0A is an intrinsic property of the dialyzer. It depends, your efficiency of the dialyzer is measured with K0A. It goes all the way from 400 to 1600. So these are low efficiency dialyzers. These are high efficiency dialyzers. So what I want to show is here, the x-axis is the blood flow rate. So when your blood flow rate is low, say you're dialyzing everybody at 200, irrespective of whether you have a really bad dialyzer or a really good dialyzer, the amount of clearance you're giving is more or less the same. The y-axis is the clearance. So your clearance is somewhere between 120 to 160 ml per minute if your blood flow is only 200, irrespective of whether you have a good dialyzer or a bad dialyzer. But when you increase your blood flow to 500, so when you really raise your blood flow rate, that's when the curves separate. That's when you see the benefit of a high efficiency dialyzer. So what I'm trying to say is, so the low bad dialyzers still give only 160 ml per minute, but the good dialyzers, 1600, that gives you around 300 plus ml per minute of clearance. So what I'm trying to say is if you have a very good dialyzer, very high efficiency dialyzer, you're wasting it by giving a low blood flow rate because you're not actually realizing any of the benefits of that high efficiency dialyzer. The true benefit is seen only at high blood flow rates. It's like the difference between a Maruti and a Ferrari. If you're in Saukar Pit in the in peak traffic, your both cars are not going to be moving. But if you move to the say the freeway or the highway, then you'll see the difference between a Maruti and a Ferrari. So in the same way, when you have a bad and a good dialyzer, if you're running low blood flow dialysis, all of them are going to have poor clearance. You need to raise the blood flow because that's a very important determinant of clearance. And this is something we should keep in mind when we are dialyzing our maintenance dialysis patients. So again, Daugirdas tells us how much we should keep the blood flow rate. So for intermittent hemodialysis, please note, he says 250 is the minimum blood flow rate. He says go all the way up to 400. So in different places in Daugirdas, they say people dialyzing at 350 ml per minute. So these are very high blood flow rates, but this should be considered the norm. In fact, even in CRRT, look at the blood flow rate which he's suggesting, 200 to 300. So a lot of us sometimes dialyze 100, 150. He actually says you can go 200, 300, and I've done that also. So, I mean, people do tolerate it well. The thing we always fear about when we raise the blood flow rate is that may induce intradialytic hypotension. Now, this is actually a misconception. Blood flow rate does not cause hypotension. This is, again, a very practical aspect which we should remember when we're talking about urea kinetics. Raising the blood flow rate does not cause hypotension. And there's this very nice paper which you can maybe read later. He says there are certain mistakes that we make in dialysis, and one of those mistakes is lowering the blood flow when there is intradialytic hypotension. He said this was true several decades ago, maybe in the 80s, because of various changes in dialysis technology. Right now, in contemporary nephrology, raising the blood flow rate does not cause hypotension or intradialytic hypotension. So this is a very important paper that maybe you should, if you haven't read it already, you can maybe read this. It's very fascinating. So these are the determinants of clearance. The time on dialysis, yes. Also the blood flow, the dialysate flow, and the K0A. So now finally we will come to the net protein catabolic rate. We said we'll come to this, the NPCR. So yeah. So the net protein catabolic rate, what this means is, so there's a difference between total protein catabolic rate and net protein catabolic rate. All right. So for example, assume that there is 100 grams of protein, which is being catabolized every day. So that's the total catabolic rate. But say 50 grams of that 100 grams is going back into anabolism. All right. So then your net protein catabolic rate is 100 minus 50, which is only 50. So though your total protein catabolic rate is 100, 50 is going into anabolism. So your net rate of catabolism is only 50. So that's the difference between total and net PCR. Why is this important? Because urea generation, basically G, has a very well-studied relationship to NPCR. All right. So urea generation G can be identified using urea kinetic modeling, and we'll see how. So with that, you can calculate NPCR. And what's the importance of NPCR? We assume that patients are in a steady state. So for people who are in steady state, catabolism equals to protein intake. So basically, protein intake equals catabolism, and catabolism can be calculated from urea generation. So this basically gives you an idea of the nutritional status of the patient. So urea kinetic modeling not only tells you about the adequacy of dialysis, it also tells you about the nutritional state and the protein intake which your patients are having. So there is actually a correlation between the NPCR, which is the protein catabolic rate, and the KT over V. So there's a linear relationship. But Henrich argues that this is an artifact. This is not necessarily causal. And he gives you reasons why this association is not true. He says all of this is based on observational data. So patients who are having a high protein intake, they naturally get prescribed a higher dose of dialysis. So obviously the two would correlate, even though it is not causal. Second thing is both of them are determined from the pre-HD urea and the post-HD urea. So by simple coupling, the two values would be similar. And finally, we have RCT data that better dialysis, giving a higher dose of dialysis, actually does not improve nutrition. We have that from the hemo study. People who got 1.6 did not differ from the people who got 1.2. And the frequent hemodialysis network data, where people who got daily dialysis or nocturnal dialysis, they did not actually have improvements in their nutrition or their body mass. So this correlation between NPCR and KTOV, some people would say, oh, he's badly nourished. So maybe if we give them a lot of dialysis, high dose of dialysis, then the nutrition will improve. So it actually doesn't work that way. So anyway, now we've finished those few concepts. So we'll come to actually what is urea kinetic modeling. So basically, we're trying to get this graph. And what this graph is showing is during the first 4 hours of dialysis, your urea drops. And then in between 2 dialysis sessions, your urea starts to rise again. So you'll see this curve, this part of the graph is slightly curved. And this reflects the first order kinetics of dialysis, meaning at high rates when the blood urea is high, the amount of removal is also high. But as the urea falls, the amount of urea removal becomes less. So your thing starts to curve. Meanwhile, your urea production is at zero order kinetics. So meaning it is independent of the blood urea. So that's why it's a straight line. So this is first order kinetics during removal and zero order kinetics during generation. So what is urea kinetic modeling? It's basically a mathematical simulation of urea flux, which is based on measurements of concentrations before and after intermittent hemodialysis, which allows the calculation of urea clearance during hemodialysis and urea generation between treatments. So we'll come back to what that is. Basically, before that, we need to know what is a single pool and what are multiple pools. So we said that there is this thing called the total body water. So the assumption here is the total body water is always accessible to dialysis, meaning the total body water is in continuous communication with the dialyzable plasma volume. So all of the body water is in a single compartment. This is the assumption that we make. But the reality is that there are actually multiple compartments. So the water is not in one single compartment. There are areas where urea is sequestered, where it is not available for dialysis. It's not accessible to the plasma. This may be in muscle, it may be in bone, it may be in skin. But they are in continuity with the plasma space, but it takes some time for it to equilibrate. And we'll talk more about this in a subsequent session maybe. But these multiple components, this is what, if you take this into consideration while you are modeling urea, then this is called the multiple compartment model. But what we are usually, and in this talk, we will restrict ourselves to the single pool model, where we assume that the total body water is in a single compartment. There is no sequestration of urea anywhere in the body. So this is the equation, the generic equation for first order kinetics. So the d by dt of C, that is the rate of change of C, C being the concentration of the solute, is proportional to C. All right, so I think we'll all remember this from long ago, physics. So first order kinetics is basically the rate of change of something is proportional to that thing. And then when you get rid of the proportional, you make it equal, you have to add a constant, and then you can do some few mathematical changes, and then you get this kt over v equals the natural logarithm of C0 by Ct. All right, so the pre-HD divided by the post-HD urea. So it's important here that absolute values are not important. It is only the ratio which is important. So if you remember that previous example which I gave you, 200 to 100 versus 100 to 50. So the absolute values don't matter. The ratio for both these patients is 2. So 200 by 100 is 2, 100 by 50 is also 2. So it doesn't matter that you've removed more urea from one person. The ratio is more important in determining the clearance of dialysis. Again, this is a very simplistic equation. It does not consider ultrafiltration. It doesn't consider residual renal clearance. It doesn't consider urea generation. So if you were to consider all of those things, then you would get this is basically the equation for single pool urea kinetic modeling. So this takes into account all of those variables which I mentioned. So C0 is the pre-HD urea, V is the total body water, B is the ultrafiltration and the weight gain, T is the time, K is the clearance. So if you put all of this together, this basically mathematically models this graph, which is what we are trying to calculate. So this is the flux of urea. All right, kinetics itself means the movement, the change. So urea kinetic modeling is basically getting this change, this graphical change through mathematical modeling. So what we have here is, this is the first session of dialysis during the week. So C0 is the pre-HD urea, CT is the post-HD urea. And this drop defines the KT over V. So the amount of clearance you have achieved during dialysis. Over the next 2 days, your urea generation kicks in. So your urea starts to rise. Before the next dialysis, you have a C0 prime, all right, and then it goes back down. Now, between these 2 sessions of dialysis, the total area under the curve, all right, so this is the area under the curve, that is basically the timed average concentration of urea. And then you give him 3 dialysis sessions. And the final assumption we make is that all these patients are in steady state. So at the start of the week and at the end of the week, their blood levels are constant. All right, so they go through all of this flux, but at the end of the week, they are back to where they began because these patients are in steady state. So we'll go into how we use this formula. So this is basically, again, the definition of urea kinetic modeling. It is a mathematical simulation of urea flux. All right, so it's the mathematical simulation of the graph, the urea flux, based on measurements of concentrations before and after intermittent hemodialysis. So you're going to measure only C0 and CT. It would actually make life a lot easier if you measured this also, but we don't. Okay, because as you know, we measure only pre and post HD urea. There's a way to bypass that, and we'll come to that. But the only things you're measuring are C0 and CT. All right. So based on measurements of concentrations before and after intermittent hemodialysis, and this allows the calculation of urea clearance during HD. So the KT over V as the graph falls, and the urea generation between treatments, the G as the graph rises. So how do we do this? What is the mechanism? So if you look at that long formula, there's 3 things that we don't know. We don't know the volume of distribution, we don't know the clearance, and we don't know the urea generation. So how do we get to those things which we don't know? There are 3 steps. It begins with the measurement of C0 and CT. So I think we all know this. I'm not going to spend too much of time. It's again very important that you use the arterial port when you are sampling blood, particularly post-HD. Pre-HD, there's usually no problem. You have to take it as soon as you prime the machine while it is being primed with blood. The CT is taken post-HD. It's always taken from the arterial line. You have to wait for 15 to 20 seconds after lowering the blood flow to 100 ml per minute. So the blood flow should be lowered to a rate where you know that it is not going to cause access recirculation, because whenever there's access recirculation, it throws all these calculations off. So you bring the blood flow to 100 ml per minute. You wait for 15 to 20 seconds. And the reason you wait is because from the arterial end of the needle to the arterial sampling port, the length of the volume of blood there is around 9 ml. And you want that to be changed at least twice before you take the measurement. So you reduce to 100 ml per minute, and then you wait for 15 to 20 seconds, and you take the sample. Alternatively, you can switch off your dialysate, run the blood flow at the same rate, and after 3 minutes, you can sample. So this is very important. I think we all know this. I'm not going to dwell on this. But this is one of the very key areas where errors are made while trying to measure dialysis. In fact, you can have errors of all the way up to 40% of your KT over V if this sampling is done incorrectly. So we should always supervise and make sure our technicians are doing it correctly. The next one is the measurement of K. So K being the clearance of the dialyzer. So as you know, all of our dialyzers, they will come with a K0A. So they will already print it and give it to you. But the problem with that K0A is this is based on in vitro experiments. So they use saline basically to run through their dialyzer and they calculate the K0A from that. Now, unfortunately, blood has a very different rheology than saline. So blood will actually coat the dialyzer, the efficiency will come down a little bit. So you need to have some correction factor for that. So that is this first step of the equation where you use the K0A, which the manufacturer tells you, which was calculated using saline, and you do the correction for blood. Step number two is you use so assuming you are using that K0A, for the current patient's blood flow and dialysate flow, what will be the diffusive clearance? So this is part two of the equation. So you enter your blood flow rate, and so QBAQ is the aqueous part of the blood, the flow rate of the aqueous part of the blood. QD is the dialysate flow. So you enter those two variables and then you get the diffusive clearance of the dialyzer for that patient's QB and QD. And then finally, you add on a correction for QF, which is basically the ultrafiltration which you are doing during dialysis. So these three corrections need to be made. And then you have your K, which you can use for KT over B. So let's talk about that ultrafiltration. So what is the effect of ultrafiltration on clearance? I mean, if you think about it, I did not realize that ultrafiltration will be causing any issues with clearance, but it does. The reason being, so this is the graph I showed you. It comes down as a curved line because this is first order kinetics. It goes up as a straight line because this is zero order kinetics. But look at this graph which was modeled. So this is actually not showing a straight line. It's slightly curved even while going up. So this is different from this graph. So why is that curve there? That curve is because of fluid gain. All right. So between Monday and Wednesday, this is how it should be. All right. This is how you expect your urea level to go. But between Monday and Wednesday, you have now gained 3.5 liters of fluid. So that 3.5 liters actually dilutes your urea. So it comes down a little bit. So that's why the curve is slightly sloping upwards and it's not reaching the peak which you expected it to be. So simply gaining weight actually dilutes the amount of urea in your blood. So your burn artificially comes down. The second thing is when you dialyze that patient, when you remove that 3 liters of fluid, it's not pure water which you are removing. You're removing 3 liters of fluid, which contains urea at the concentration of plasma. So, for example, if somebody has a urea of 180 milligrams per deciliter at the start of dialysis. When you remove 3 liters of fluid, that 3 liters of fluid contains 180 milligram per deciliter of urea. So, simply doing ultrafiltration adds to your clearance. In fact, if you have a 70 kg person who is doing 3 times a week dialysis and their weight gain is 3.5 to 4 kg, the ultrafiltration alone accounts for around 0.15 to zero point 0.2 of his KT over V, just the ultrafiltration. So it's important that you make that correction. So that again is for K. First step is because your manufacturer K0A is based on saline, so you correct it for the blood. Second one, you correct it for your patient's QB and QD. Third one is you correct it for your patient's ultrafiltration, and you're left with the K, which you can use for KT over V. And now finally, how do you calculate G? All right, you need two things. You need V and you need G. So calculation of V, again, this is slightly I just want to show you how it's done. Nobody's going to ask you all of this, but it's interesting to see how it's done. Uh, so assuming somebody has a urea of 100, they get dialysis and the urea comes to 80. In this time, you have removed 20 milligrams of urea. Okay, basically you take all of the dialysate which you have used, you measure the amount of urea in that dialysate so that you know how much of urea you have removed and it comes to 20. With this, is it possible to calculate the volume in which the urea was contained? All right, and it is actually very simple because concentration is mass by volume. All right, so if you need volume, volume is therefore mass by concentration. So mass, you already have 20 milligram. Concentration difference, so C0 minus C2, CT is also 20, 100 minus 80 is 20. So 20 by 20 is 1. And the volume of this square is now 1 deciliter. So what I'm trying to say is if you have the amount of urea removed and you have the change in the urea concentrations at the end, before and after dialysis, you can calculate the total body water. So the total volume in which that urea was contained. So that's how we measure total body water. All right. So you may say we can just, why go to all of this effort? We can just use that Watson's formula, which we have. Why can't we just do that? So that is the difference between estimate. So for example, GFR. we can use eGFR using the CKD-EP equation, or you can measure GFR by doing annual clearance. So this is a way in which you measure the V. It's not estimating the V based on a formula. You're actually measuring the V by determining the change in urea concentration. So C0 is pre-HD and CE is post-HD. So this is so we said now that the volume equals the mass divided by the concentration. So the numerator here is the amount or mass of urea removed, and the denominator is the concentration. So that's how we calculate the V. And what is this integral here in the middle? So integral of C meaning the change in C as time moves from C0 to T. All right. So as time moves from 0 to T, what is the change in C? So this is when you say integral, you're basically talking about the area under the curve. So this is the part which is represented by the integral of C. And if you look, even the units all cancel out. So KT is actually volume. All right, we mentioned already KT is the volume of plasma which is cleared. Multiply that by the concentration. So liter per hour and hour cancels, and this liter and this deciliter cancels. So you're left with the numerator, which is the amount or the mass of urea. Okay, if that didn't make sense, it doesn't matter. But I'm just trying to say that the volume V here is modeled based on the urea change during dialysis. It is not estimated based on a formula. So that is step one to calculate the V. The next step is you need to know what this value is. So C0 prime, that is the pre-HD urea on the next dialysis session on Wednesday. So this is actually difficult to do because as all of us know, it's how many of us actually measure KT over V? Because I actually get pre-HD and post-HD urea in all of my patients. And even then, I don't sit and do the KT over V. So nephrologists in general, we don't tend to spend that time to do the KT over V. So if you make it difficult and say you don't need just that one value, even the next session when he comes, you need a pre-HD urea value, it becomes difficult to do. It's not going to be done large scale. So you need a way to bypass measuring this C0 prime. And that's why you have this computer program which estimates G. So basically, it starts there. KT over V, you have calculated K, you've calculated V, so it draws this line. And then it basically guesses what the G is. So it assume that G is 9.9. So then your urea rises. Okay, it's a steep rise because G is high. And then it comes down again based on that KT over V. Again, it rises, it comes down, and again it rises. Now, the problem is we assumed now that at the end of the week, he would be back to where he started. But with this G, he's ending at a higher level than he started. So therefore, this cannot be the correct G. All right. So next, the computer assumes, okay, this was too high. We'll go a little low. So now G of 7.3, it assumes. So KT over V, it draws the line. Now you see the rise is more flattened than here. Here it rose rapidly because G was high. Here G is low, so it's rising less. It rises less, it rises less. Now it ends up below where it started. So again, this cannot be true because at steady state, you need to end at the same point where you began. So like this, by trial and error, it goes up, goes down. So it's probably somewhere in the middle here. So it picks 8.3. 8.3, it goes up, comes down, and it ends at the same point. So now this has to be the true G. So this is how it is modeled. So first it selects a G, empirically just guesses, calculates the V. With that, it draws this graph. And then at the end of that graph is the last value within 1% of the start value. If it is, then that is the true value. If it's not, it changes G accordingly. And then it does this whole thing again and again until it matches. So basically, you avoid measuring this C0 by guessing G until you reach this equilibrium from start to finish. So again, nobody is going to ask you all of this. I'm just trying to show you that all of these are simple mathematical formulae which are predictable. There is no AI, there is no vague computer generation which we cannot understand. These are all simple mathematical predictable equations which are used to do this calculation. So now we've got all three. We've measured C0 and CT, we've measured K, and we've done the three corrections. We've modeled G and we've calculated V. So now you have those three things which you did not know in this equation, and therefore you're able to draw your graph. The drop determines KT over V. The rise determines your G, which is related to NPCR, which is related to your protein intake, and therefore your nutritional parameters. So this is urea kinetic modeling, and this is done by the computer. So again, we look at that definition again. No, I'm sorry. So, okay, it's not done yet. The one last thing, and I'm almost done. I'll finish in another 5 or 10 minutes. So the effect of residual renal clearance. So we've done all of this. We've accounted for ultrafiltration. We've accounted for the manufacturer's urea clearance. We've done all of this, but there is still something which we have not accounted for, and that is the residual kidney clearance. So how do you measure residual kidney clearance? This is basically you do a 24-hour urine collection. All right. And the patient comes to the dialysis center with that 24-hour urine collection. You measure the urea level in that, you measure the urine flow rate. So 24 hours, he's got 2 liters, meaning how many ml per minute has he been making. So you can do that calculation. And you measure the blood urea level at that time. So this is basically UV by P. So U divided by P into V. V is the urine flow rate. So this is how you calculate the residual kidney clearance. So the thing about residual kidney clearance, it's a very low value. It is between 0 and 8 ml per minute. And this is completely dwarfed by your dialysis clearance. So dialysis clearance, you're clearing, say a 70 kg guy, if you're clearing, let's say his total body water once. So you're clearing around 40 liters in 4 hours. So 10 liters per hour of clearance you're giving. What about residual urine clearance? It's only 0 to 8 ml per minute. All right. So it is much, much less than your dialysis clearance. So what your residual kidney clearance, what it does not affect this downslope. It does not affect the dialysis part of your graph, but the rise in urea, okay, because it is a continuous clearance, it's 0 to 8 ml per minute over an entire 2 or 3 days and throughout the entire week. So even though it doesn't affect the drop in urea during dialysis, it does affect the rise in urea between dialysis sessions. So this red line here is after accounting for the residual renal function. So why this is important? Again, it does not affect your KT over V. But if you are doing formal urea kinetics to measure G, and you're using G to use nutritional to assess your nutrition, the nutrition of your patient, then you will need to have an accurate assessment of the upslope. So that's when you add on the residual renal clearance. And one last thing about residual kidney clearance, you cannot simply add it on to the KT over V, because KT over V is an intermittent clearance. It's done only for those 4 hours, 3 times a week, whereas this is a continuous clearance over 24 hours. So there are certain mathematical ways in which you can combine the two, but it is not simple addition. So again, we're at the end of this now. So urea kinetic modeling, again, we're looking at this definition now. It hopefully should start making a little bit more sense. So this is simply a mathematical simulation of urea flux, which is based on measurements of concentrations before and after intermittent hemodialysis. And it allows the calculation of urea clearance during HD and the urea generation, which is between treatments. All right, so we've spoken all of this, but then how do you actually do it? There's this website, ureakinetics.org. You go to the solute solver. This is very simple. These are all the things that you require. You just say which days the guy is coming for dialysis. This is your residual kidney clearance, ml per minute. Pre-HD bun, post-HD bun, blood flow, dialysate flow, time on dialysis, pre-HD weight, post-HD weight, and the K0 of your dialyzer. You let's calculate, and it should give you your value. So that is the end of today, urea kinetic modeling. And let me unshare my screen. I hope that made some sense too, at least a little bit of sense. If anybody has any questions, I may not know most of it, but anyway, thank you all for staying so long. I didn't expect so many of you to be here. Hope this was slightly useful. Anybody else has any questions? Thank you, Ganapati. Okay, thank you all. Let me just stop recording.
So,
Go ahead, please tell me. Hello?
hello, sir.
Yeah, please tell me.
Uh, sir, like, how often would we be requiring this in our clinical practice? And in what ways can I use it? Like this
Uh,
one.
yeah. So actually, I think the current guidance is you need to target that SPKT over V of 1.2, and you should be measuring it at least once a month. In our unit, that's what we do. Every month when they get their labs, they get a pre-HD urea and a post-HD urea. It's just that I never calculate the SPKT over V. So this is what I showed you now is actually the long form of it. So this is what they call formal urea kinetics, which takes into account all of these numerous factors. There's a much easier way to do it. It's called the Daugirdas equation, which you'll be able to find it on QX Calculate and on Google. It requires only a few things. It requires your weight gain, I think your ultrafiltration, your time on dialysis, pre-HD urea, and post-HD urea. You put those four things into the equation and it will tell you the KTOV. So you don't need to think about all of this graph and all of these 100 things which I told you. It's actually much simpler to do. And I think you should be measuring it at least once a month. So certain patients, you may find their ureas to be low and you think you're doing good dialysis. But if you actually do the KTOV and see, you're actually not sufficiently dialyzing them. So you'll know that only if you measure it.
Thank you, sir.
Yeah, thank you. Drawbacks of KTOV. So yes, actually there are quite a lot of drawbacks with KTOV. So it depends on the way you measure it. Let me also say that certain obituaries are being written about the KTOV. There was one very nice paper. If we're having another class, I can maybe show that to you. It says that we are now in the last days of KTOV. So what they say is this all made sense in the 80s and 90s when everybody was getting 3 times a week dialysis. Everybody was getting 4 hours of dialysis. Now a lot of people are on home hemodialysis in the US. A lot of people are getting 4, 5 times dialysis. I mean, more frequent dialysis. So it and a lot of people are not getting 4 hours. So in the US and all, they target it to the SPKTOV. So some people get only 3, 3.5 hours and all. So in those situations, KTOV may not apply. The second important drawback is it is very urea centric. So basically, if you are making that assumption that if you are clearing urea, you are also clearing all of the other uremic solutes. That also has been found to be untrue. So, I mean, it's the best we have at the moment to assess dialysis adequacy, but it does have all of these drawbacks. Uh, so, can you elaborate on NPCR? So, yeah, okay. Let me just share that one slide again then. So, NPCR, yeah. So, basically, we were speaking about the net protein catabolic rate. All right. So urea generation, as I said, through urea kinetic modeling, we get a value for G and we can calculate this protein catabolic rate from G. When we know G and V, we can calculate the protein catabolic rate. And in any steady state person, protein catabolism should be equal to their protein intake because they are in steady state. That's the assumption we make. So protein intake equals NPCR. So NPCR is basically a surrogate for how much your patient is eating, how nutritionally well they are. And that is dependent on G. So you can use that rise in G to quantify your protein intake and nutritional status. So again, that only comes with your formal urea kinetic modeling. It doesn't come with your Daukidas formula. I hope that made sense. Why is KT over V not so useful in women and children? Yes, that's a very good question, Dr. Soumya. So the problem here is, so for example, creatinine, let's take creatinine. Most biological parameters are actually normalized to the body surface area, not to the total body water. So for example, when we take creatinine, and when we measure GFR, we say 90 ml per minute per 1.73 square meter. So you're normalizing it to the body surface area. Most metabolic functions correlate with body surface area and not the volume of distribution. Here we have been using volume of distribution because it makes the calculations actually a little easier. So what they found is that there's a discrepancy between V and BSA for women and children. So that's why KT over V is not so useful for women and children. In fact, they require a slightly higher KT over V compared to men and larger adults. So giving 1.2 to a woman or a child may actually be slightly inadequate. It is not the same amount of dialysis as the other people because of this difference between V, that is the total body water, and the body surface area. So in fact, there has been a suggestion that you can normalize KT to BSA. So KT by BSA is another thing which was muted, which was studied. But I think as of now, we are only doing KT over B. But that's the issue with women and children. I hope that answered the question. Right. So thank you all. I didn't expect all of you to stay this long. If there is a part 2 class, if anybody is interested, we'll we haven't spoken about equilibrated KT over V, standard KT over V. There's a couple of other things. Maybe another day, if people are interested, we can do that. Okay, thank you.